Good morning. We're going to build on the concept that we covered in the last lesson, which is finding average rates of change where our intervals are getting closer and closer to an instant. So we made our intervals smaller and smaller. That concept is a limit. So we're going to go a little bit more in depth with limits and how to find them numerically and graphically, one-sided limits that don't exist, and functions that approach infinity as a limit. Before we do that, let's look at a situation. So how do the values of a function f of x behave when x approaches a number c, whether or not f of c is defined? We're going to start by experimenting with the function x, where x is in radians, f of x equals sine of x over x. Now, if we consider the value x equals 0 and plug this in, sine of 0 over 0 is undefined. However, if we look at the graph here of that function, you'll notice when I click here, it does say undefined, if I can get in the right spot. So it's undefined there. But we could look to see what happens as our function gets closer and closer to where x equals 0. And you'll notice that it is defined until we hit that point, which is really close, or if I plugged it in, would be at 1. Okay, so if I look at this, it's getting closer and closer to 1 there. So that's what we would use for a limit. Okay, whoops, sorry, wrong spot. Okay, so what we notice is that if we get closer and closer to 0, from the right side, the value gets closer and closer to 1. And if we approach 0 from the left side, it is also getting closer and closer to 1. Okay, this is important notation here that you need to make sure you know. If the plus sign is after the number, that means from the right. Minus sign is after the number, it means from the left. So this gives us the same information we talked about. Even though this isn't defined here, as x approaches 0 from both sides, our limit is 1. And so our notation here is the limit as x approaches 0 from both sides, because it doesn't have the signs there, of the function is equal to 1. Okay, so here's your definition. Assume that f of x is defined for all x in an open interval containing c, but not necessarily at c itself. We say that the limit of f of x as x approaches c is equal to L. If the absolute value of f of x minus L becomes arbitrarily small when x is any number sufficiently close to but not equal to c. In this case, we write the limit as x approaches c of f of x equals L. We also say that f of x approaches or converges to L as x approaches c. Okay, a lot of math jargon there. Okay, let's do this. We are going to use the definition of a limit above to verify the following. So we're going to use the idea that a function, which is right here, minus the limit L should get closer and closer to 0. The absolute value of it should get closer and closer to 0. So we're going to do the absolute value of f of x minus 5 equals 0, or gets closer and closer to 0. And I'm actually not even going to write it that way. Okay, so we're going to look at this. So if my function is always 5, no matter what I plug in, 5 minus 5, absolute value, is always equal to 0. So for all x, we have verified that that works. For the second one, our function is 3x plus 1, and our limit L is 13. So what we're going to do is we're going to do 3x plus 1 minus 13, and we're going to see what happens when our values get closer and closer to 4 here. So simplify this, 3x, combine those, I get minus 12. And I can actually factor, because I'm going to factor out a positive number here. So if I divide everything by 3, I have the absolute value of x minus 4. if I plug values in that are getting closer and closer to 4, for example, 3.5, 3.9, and 3.99, and figure out those values, they should be getting closer and closer to 0. So 1.5, 0.3, 0.03. So those are getting closer and closer to 0. Just verified. Next one. We have a theorem. Okay, so essentially what we just verified is that the limit as x approaches any number c when we have a constant is always going to be that constant. And the limit as x approaches any value c of the function x is the same as c. Graphical investigation. We're going to use a graphing utility to produce a graph of f of x, and then we can use that to determine if a limit exists or not. And then for numerical, we're going to make a table of values and use values that are close to x that are less than and close to x that are greater than, so approaching from the left and the right. And if they both get close to the same number, we'll be able to estimate the limit. Okay, so for the first one, I'm going to go ahead and investigate this graphically. So we have x minus 9 over the square root of x minus 3. Okay, so here's our graph here, and I like Desmos because I can move this around pretty easily. So looking at this graph, the limit as x approaches 9 in my graph is right here at 6. Okay, so graphically, when x is 9, my function is approaching 6. Let's verify that numerically. So I'm going to go ahead and pick some values on the left side and on the right side and plug them in. So on the left side, we are going to go ahead and plug in values that are, switching colors there, getting closer and closer to 9 from the left. So I'm going to do 8.5, 8.9, and 8.99. And I'm going to do the same thing on the right. And I'm going to do 9.5, 9.1, and 9.01. So those two numbers on the bottom should be the closest of anything. I'm going to go ahead and plug those numbers in. So when I plug in 8.5 in my calculator, I get 5.915. When I plug in 8.9, I get 5.983. And again, I'm just plugging those in for my x values. And I plug in 8.99, I get 5.998. Same thing on the right side. If I plug in 9.5, I get 6.082. 9.1, I get 6.017. And 9.01, I get 6.002. So notice, if I were to extend this out and actually take it one step further, I'm getting really close to 6 for both of those. So we just verified that numerically. We're going to go ahead and pause this or stop this and switch to another video to kind of keep this short. If you have any questions, don't hesitate to ask.